All right, let's go. Cool. Okay, we're good. Ready to go when you are.
All right, let's get started. So welcome to another installment of our graduate seminar series. It's a pleasure to introduce to you today's speaker, Professor Michael Keller, across the hall from us in Stevenson at Mechanical Engineering. Professor Keller works in a lot of interesting areas. He's also a good friend and collaborator. I consider him a friend, at least. Dr. Keller earned his doctoral degree at the University of Illinois at Urbana-Champaign. And before that, he was a TU student in the undergraduate program here in Mechanical Engineering. Dr. Keller is the recipient of several awards. A notable one is the NSF Career Award. So we're really proud and happy to have him as a colleague here at TU. So without further delay, Mike,
thank you, Professor Yunus. I appreciate it. So like you said, I'm Mike Keller. I'll actually, you mentioned career, and I'll talk, most of the talk's actually going to be on some of the research that we've done for career, but then we've sort of continued to expand on this topic and actually through a collaboration with Dr. Yunus and then some other members at TU and elsewhere have actually sort of expanded a little bit into energy production and sort of related fields. But we'll cover that sort of the end. So try to get a little bit of flavor of that. It's not just a straight up composites talk, which is near and dear to my heart, but not everybody shares that one. So just a little bit about the research that my group does here at TU. And so like my general idea, actually my PhD is not in mechanical engineering, it's actually in theoretical applied mechanics. So what I try to do is I try to use mechanics to inform the processing and synthesis of sort of multifunctional composites and materials. So what I want to do is I joke that material science sort of lives in two places. It lives in make it and then break it, right? So you have people that are synthesizing and processing new materials, and then typically the people that are breaking it through tensile tests, mechanical tests, or other characterization processes, right, to understand what is going on and the interaction between those two things. And I try to use both of those two sides of my sort of personality, academically speaking, to help me drive new material development and synthesis for a range of environments. Spend a lot of time focusing in aerospace, but I kind of don't care what the internal application is, right? I'm more just interested in making new stuff. And so these are sort of some of the things that go on in my lab. So this is I'll talk broadly about these two things in the talk today, which are related through a shared manufacturing method or manufacturing concept, I guess. Maybe the method's different between the two, but this is an image of a non-destructive evaluation or sort of a way of understanding if something is damaged using a nanoparticle contrast agent. This is sort of the career grant. And then this is some work that we're doing through a DOE-supported grant trying to create microvascular composites intended for solar receivers. So we'll talk a little bit about that in a little bit. And then other stuff I do, I work on materials with sort of tunable function or tunable mechanical properties intended for soft robotics, and I do a little bit with sort of biological materials and bio related stuff as well. This is more of a hobby, to be fully honest, but that's cool. All right, so why do I care about, or why as an engineer do we care about sort of non-destructive evaluation or damage detection, and also prevent perhaps damage repair in composite materials? So the answer to that is in this picture right here. So this is a fiber reinforced composite, and that fiber reinforcement, right? You see all those little dots there, right? Those are the fibers coming out at you from the screen, right? But then these are some in plane, and then in plane here too. And what you'll notice is this crack, right? So composite materials, carbon fiber, fiberglass, Kevlar, whatever you want to think about it, are really engineeringly exciting, I guess, in some sense, in the sense that like I can tune material properties by adjusting proportion, changing the materials. I can make things that are very light, but have really high specific modulus and specific strength, right? To the point where, right, this is a Dreamliner. The cool part about the Dreamliner is it's mostly carbon fiber, right? And And so that makes it really light, increases fuel efficiency, right? We have a twin-engine small aircraft that can do, Pacific flights, no problem, right? We don't need the giant 787 or whatever it is, the one with 4 engines, right? The really big aircraft is a much smaller aircraft. I'll tell you, they're super quiet, but they suffer from the problem or there's a baked-in problem in using composites in these sort of structurally critical areas, especially the fuselage, and that these cracks can form that you see here without any indication and deep in the structure, right? So this is inside the material. It's not obvious. The cool part about metals is when it cracks, it goes pretty much all the way through the metal, and you can see it usually, right? But here, I can't see this. I don't know this thing is damaged, and I can reduce the overall strength of the material by like more than 50% in an instant. Let's say I have an AMP mechanic that's working somewhere on here, and he drops or she drops a wrench onto the wing surface. I've suddenly introduced a massive cone of damage underneath that material with almost no visible surface damage at all, right? And so now I've severely compromised my structure, and I don't know it, and then we go flying and we lose a wing or something, right? So in some sense, right, with great knowledge comes great fear, right? So every time you get on a plane, right, you look over that jet engine and there's metal going at 800, like 500 C, right, spinning at multiple thousands RPMs, and if we blade out, like, it's going to be a thing, right? So it's really scary. But you do it because you're like, but we're cool, right? And so do I. That's the inside of a Dreamliner cockpit. I was really excited. I ran up through first class. I didn't get tackled. Post 9/11, so that's good. Anyways, and I was like, can I see the cockpit? And then they let me sit in it. Anyway, so I still get on these planes because I'm pretty comfortable with the testing and our understanding of how these materials develop, right? So the way that we address this type of stuff right now is we test the crap out of it, right? We go through and we run test after test after test so we can get a really good statistical understanding of the material. So when I actually put it into service, I am comfortable that I've designed this such that I'm well below the statistical limits or material allowables, right? And the material will survive. And this is a really cool plane. If you've ever been on one, the wingtips flex like crazy. The engines actually come up above the fuselage. They also have cool electrochromic windows. It's also the quietest plane I've ever been in my entire life. So, despite my fear that it's going to come apart at any minute. Okay, so how do we? So I've said we test the crap out of it, but a cooler way to do this, right, would be to build in a resilience to the material, right? Design the composite material so that it does something in response to the mechanical damage to either mitigate this damage, keep it from propagating, or ideally reverse it, right? That would be cool. And so we ask ourselves, right, how do we, if I look around myself and ask what in the world or the universe repairs itself when damaged, and the answer is you do, right? I cut myself, right? I bleed, and when you bleed, right, you scab. And then you have the scab, and then your body starts remodeling underneath the material, and then finally you end up with a scar, right? And this is a really complicated process, right? This process alone, right, there's all these like cofactor cascade things to prevent clotting from happening where it shouldn't, right? Because like clotting in a cut is good, clotting in your brain is a stroke. We don't want that, right? And so we try to avoid. So your body has a very complicated system to avoid that from happening, right? And so when we start thinking about taking inspiration from nature, you can go sort of two routes, right? You can go full biomimicry, right? I'm going to create a thing that behaves like biology. And that would be like, recovering this type of thing, right? And doing all that other type of stuff. And that's complicated, and there's reasons why you might want to do that. But in general, we don't really care. This is too much, right, for what we want to do. And so we go to bio-inspired, right? And I look at this Ford thing, and I pulled this from a internet website so long ago that I have no idea whose it is. So if you're in the room, I apologize. But I look at this process and I go, well, I can do this. I can cause something to bleed, perhaps, and cause it to clot. This steps B through D are beyond us, perhaps, right now. But we're looking to maybe see what we can do. So how do we do step A? So the way that we do step A is through sort of three possible approaches. Okay. So the first approach would be to use microcapsules. So I take little spherical polymer shells, I fill them with glue. The damage breaks it. They crack those microcapsules off. The liquid pulls out, and then it mixes like an epoxy, right? Part A, part B, you have a reaction, you bond the two sides together. Okay, that's what this material is right here. The other option is you build a synthetic vasculature. I build fake blood vessels in a synthetic material. I flow healing agent or whatever through it, right? Same process. And the third way is more like your body. I design the polymer or the material to heal intrinsically, right? So I think about creating either a reversible polymerization process, supermolecular polymers that are held together not by covalent bonds, but by van der Waals forces or hydrogen bonding or something like that. Bonds that are inherently reversible, right? So when you cut, it sticks itself back together again. Okay. All right. So we sort of live in this two space in my lab. This is interesting to me, but I'm not a polymer chemist, so I don't really work in this. But we sort of apply these two techniques. This is sort of the very first self-healing polymer that's down in like 2002. And then this material right here is actually a damage detection system where you can see this cut, and then the color starts changing, and you see this sort of bright red, material working there. So I'm going to talk to you a little bit about two approaches that we've done using magnetically functional materials in this space before transitioning to the other. Okay. So the first thing that we did with this was to just sort of recreate that structure. And our goal here is to take microcapsules that we make through a really sort of simple process, and we incorporate a nanoparticle. So an iron oxide nanoparticle, right? Iron oxide comes in a lot of different flavors, right? So this is a magnetite-magnemite form of the iron oxide, which is also like lodestone, right? That's sort of that mineral, so it's magnetic or paramagnetic. We were able to make microcapsules where we incorporated that. You can see the capsules here stuck on a magnet. And then it's also kind of cool, if you look here, you can see this is a razor blade that's been magnetized. You can watch all the nanoparticles like come to one side inside the individual microcapsule, right? And so what we used these for was to think about directed placement of the microcapsules, right? So in many self-healing materials, these microcapsules, the chemistry within them is quite costly. And so if I'm interested in putting microcapsules in material, large-scale structures, right, it would be better if I could place them direct, like in an intelligent way, right? And so we do that. And so what you can see here is, right, this is just when you mix. So this is an epoxy specimen, and an epoxy writes two liquid resins. You have a part A and a part B mixed together, and then you walk away and it cures up into the hard polymer. So what we do here is we simply add the capsules like powder, mix it up, right, and you get sort of like baking cake. And then you end up with this like statistical distribution of particles, right, because it's random. When we use magnets to drive them, we can locate them along where we know the crack is going to go. This is a fracture specimen. We use fracture almost always when characterizing healing, mainly because that's the weak link in most epoxies and structural components. So what happens here? So really what happens here is this is fun demonstration. And what we were able to do is what you're really doing is you're locally concentrating the healing agent, right, where you want it. And you can make really big gains in healing efficiency or healing capability with tiny amounts of material. So this is a complicated plot, so we'll walk through this. So ignore this for right now. And so what we have on this y-axis here is a thing called healing efficiency. So this is a fracture toughness measure. So this is the first fracture test. Then we stick it together, walk away, let it heal. Then we do another fracture test. And it's simply the ratio between the second test to the first test, right? So if I have 100% recovery, if I break it and I get 20 Newton square root meters, right? And then I walk away, let it heal, break it again, and I get 20 MPa square root meter, then that would be 100% healing efficiency, right? Or if I got 100, it would be 50%. So that's what you see here, right? 100% down to 0, and then nominal microcapsule concentration by weights on the bottom. And so what you see here is if you just mix them in, like I was talking about as a powder, right? At about 0.28%, we go to 0. Essentially, there's not enough microcapsules to heal anything, right? But because we can drive them around, we can actually get well below 0.2% and still get repair. And what you're seeing, these giant bars, is at this point, we get some that don't heal very well and some that heal okay, just because there's not that much. And actually, we had to cut off down here like 0.02% because we couldn't physically measure the microcapsules efficiently anymore. There just weren't quite enough of them. And so what you see, right, when you look at the fracture surface in SEM is this is the statistical mix, and you see just a few capsules, but then when you concentrate them, right, shockingly, there's a bunch of them right there. So this was just a fun toy that we were demonstrating that we could do. The actual idea had initially been to complete the next work, and we'll look at that. Anyway, so the idea that we were trying to drive at that sort of led that was to create nanoparticle contrast agents. So in biomedical, I kind of imagine this as taking, right, a lot of time we take engineering ideas and push them to medicine. I was trying to think, oh, can I use medicine ideas to like diagnostic tools to come back to synthetic materials? And so we were looking at, I was kind of looking through, and this is a rat kidney. So here's a rat kidneys. There's the rat spine. And what you see here is the urethra, or urethra, no, not the urethra, urethra, or something like that. Anyways, it's the drain line, right? So your kidneys are producing urine, right, in the rat, and then it drains down your bladder. And so these are the channels that connect your kidneys to the rat bladder in this particular case. And this is an X-ray, and they're completely invisible in X-ray. But what they did is they injected their rat kidneys with nanoparticles, gold nanoparticles. And so, right, the contrast agent's really high, and so these are, you can see it now, right? So these are like a couple microns or something, or 2, 3, or 4 microns in diameter, right? Or maybe 20 microns, a little bit bigger. So now you can see it. So my idea was like, could we use these iron oxide nanoparticles that we could encapsulate to highlight damage? Could I, right? Because again, damage is a hole, right? And if they're liquid suspended, they should carry, right, into those damaged regions. How do we normally do non-destructive evaluation in composites? Well, we use ultrasound, thermography, superconducting magnets. You can also use X-rays. These don't work so well. Ultrasound is the gold standard. So, and it's the gold standard in most non-destructive evaluation, no matter what metal it is, or material it is, sorry, metals too. But it sort of is complicated, and to have the best choice, you have to have access to things. You have a coupling media that's challenging. It can be kind of slow. The equipment can be big. This is a thermography works pretty well, but there's other issues because it's hard sometimes to distinguish between structure behind and damage. So what you're seeing here is my grad student holding a composite panel that's been damaged, right? So you can see that there's a thermal conductivity because there's air, right, in the gap, so the thermal conductivity is all right. For composites, there's this type of stuff that goes on. So there's a magnetic reluctance. So you can do a magnetic detection on carbon-carbon fiber composites, but it only works in a region, a thin region, like a millimeter at the surface. Many composites are much thicker than that. You can do color change. Again, there's some microcapsule-based methods. We saw one, right, in the initial system. And this reaction leads to color change. You can do an evaporation of a solvent out of material that causes some sort of material to fluoresce. But the key point, right, is all of these things are essentially surface techniques, right? If I have damage on my surface, I can see it, right? But it's on the surface. You should be able to see it to begin with, right? So maybe this isn't so useful. The other option is sort of fibers as sensors. So there's fiber Bragg grading sensors. You can embed strain gauges basically into your material, or you can look at carbon. Carbon it's electrically conductive, right? So if it breaks, its resistance goes up, right? So you can measure that as well. We decided to use this magnetic contrast agent, and the goal here was to take the nanoparticle chemistry, which we can see here, and basically have it react in situ in the damage. So to make magnetic nanoparticles, it's actually really quite easy. You take an iron salt solution, like an iron chloride solution, you take a base, and you mix the two together, and it precipitates out iron oxide nanoparticles under the correct conditions. Usually you have to mix really fast. That's it. It happens really quickly. It produces these things, and you can see we can do it. This is sort of an in situ demonstration where we have a piece of damage here. You can see this, and then the encapsulation. So how do we do this? The way that we did it was we created channels through a really low-tech process. So here's my carbon fiber. Here are some Teflon-coated wires. We basically laid the thing up, and then we yanked the wires out of it, right? And in such, we created a vasculature, right? So now I have channels like blood vessels that are sitting here, and we can then flow material in. Then we did an impact damage. So a couple of my grad students built an instrumented or quasi-instrumented impactor. Cool little watch, pneumatic stoppers. It keeps it from hitting it multiple times, which is fun. I was very proud of them. And then this is a real-time video of us injecting the solutions. So it forms these magnetic nanoparticles in seconds. And you can see that bruise growing, right? So that tells us where it's damaged. So once we had done this, we were like, aha, we can do it, right? So the question then that we had to answer was, how good is it, right? Because that's the critical question. So pretty good, actually. So we can interrogate this in sort of three ways. You can take a visual image, right? We can do a magnetic sense, right, which was the initial goal. And we can also thermally detect it using inductive heating, right? Because in fiberglass, right, inductive heating doesn't do anything because it's non-conductive. Carbon fiber does quite a bit because the carbon fibers are conductive, right? So this is like not right out for carbon fiber. But for these two things, it's can. And the critical point is this composite that we're imaging here, that you sort of see in this composite image, I like to refer to these as data collages, is like more than a 1/4 inch thick, right? So we're 6 millimeters or something, right? Or 3 millimeters or 4 millimeters from the surface of the damage, right? And so we're actually imaging sort of in the middle of the composite. And what you have here is this is an ultrasound measurement of this visually taking a picture. So this is it undamaged, this is the material injected, this is the ultrasound, and so you can see this dark region that represents the damage that was prior to us injecting it. This is our thermal image, so you can see a thermal piece here, and then this is a magnetic scanning image. And this magnetic scanning image is a little messy, but this is sort of magnetic flux measurements that we do. And if we take the C-scan composite as the baseline, i.e. 100%, right, we can see that the visual detection, us just taking a picture, drawing an outline, and measuring the total area, right, actually that's pretty good, right? I'm like pretty psyched. The concentration, low, high concentration, this generated more nanoparticles. We just had a higher salt concentration. Magnetic does better. We get, even at the low concentration, essentially we're statistically indistinguishable from C-scan in the magnetic detection. Thermal is messy because we're heating it, and as we heat it, it grows, right? So you kind of have to pick an arbitrary choice, right? So anyway, this is a little messy, but it was kind of fun to do. In fact, I'll show you a little bit how we did it, because building the system to measure that was sort of the game. All right, so the nanoparticle production, the question that we had was like, are the nanoparticles real or is it just junk, right? Is there some way we can prove it? So we sectioned it, and then we looked at the nanoparticles under TEM and SEM, and they actually look quite good. So we have these sort of 40 nanometer particle pieces and sort of agglomerations and then some sort of individual nanoparticles. So they were pretty similar to the nanoparticle structure that we would produce in a controlled situation. This was a completely uncontrolled stoichiometry, right? We just injected it and let it mix however it wanted to. So we were pretty psyched about that. How well does the visual damage? So this is a photo collage of that same section. So what we were doing is we were sort of zooming in at these crack tips to figure out how far the nanoparticles got in here, right? So our initial thought when we first were designing this was to put microcapsules filled with nanoparticles in the material and then have it break and then come out. But the reality is the nanoparticles are they're sort of amphiphilic, right? They have hydrophobic and hydrophilic content, and they sort of thermally irreversibly adhere to the interior of the surface, and they don't come out. So we had to switch to this other approach. So, but we'll talk a little bit more about what we do. So what you can see here is our nanoparticle coverage goes pretty close. Like we get to within about 1 millimeter of the actual crack tip, just due to capillary motion out. So that was pretty good. We were pretty psyched about that. So it does a pretty good job. And then obviously right through this large area of delamination, you can see right where the channels went up. We did pretty good. And unsurprisingly, the damage region is on the tensile side, right? So we hit here, it thins up, right? So we get most of the damage on that tensile. The magnetic scanner, we built this sort of 2D scanning system to run over the system, and we calibrated it and did all that other type of stuff. And so that one worked out pretty well. You saw the damage. That was the one that was almost 100 statistically indistinguishable. The funny thing that we had to do is we moved the sample. So right, the detector stays fixed, and we moved the sample over it because it vibrates. But you got to be kind of careful with it. So that was an interesting, fun project to do. What we were able to determine is this is pretty concentration dependent up to a point. So we need to make sure that when we're doing the magnetic, when we're making the magnetic nanoparticles, right, we've got a sufficiently concentrated solution, because our detection accuracy falls off if we're not producing a fairly large number of nanoparticles, right? Because essentially we have to get them to track out there via capillary action as the liquid flows out to the crack surfaces. So in here, you can just see a couple of simulations of sort of like a higher concentration versus a lower concentration. We had a thresholding process where we sort of, above a certain threshold, we just define that as the edge, right? The thermal sensing was, to be fully honest, probably doesn't have much practical aspect, but it was a fun, like, sort of can we do it type of thing. And so we used induction heating to heat the contrast agent, so it's just locally heated. What we found is, right, the nanoparticles are really small, and there's not a lot of mass there, and so the switching frequency has to be super high in the induction heating, right? So the induction heating works by alternating the magnetic field direction back and forth, and you get sort of Joule heating or just sort of frictional heating. And so we had to have something like greater than 400 kilohertz, and we actually had to push it to nearly a megahertz of switching. That's something you can't buy commercially. So we picked up an induction heating board off of Amazon. We hot rodded it with capacitors designed for welding units. We immersed it in a mineral oil cooling bath and ran it that way. So it was kind of an aggressive process. It took my poor grad student, like a better part of 3 months to build this thing. We kept blowing up capacitors because of heat, but eventually he got it done, and we built this little pancake coil, and we're able to get these detection things. And so you can just see, as you would expect, the temperature rises as like the hotspot expands as time goes on, right, as the sort of heat conducts outward from the local region. And you can kind of see it gets sort of a steady state. I mean, it hits a point where the balance between the heat production and then the natural convection, right, and all that other type of stuff gets balanced, and we reach a steady state. But you can clearly see the damage size increase. I will say, like, it takes like 20 or 30 minutes of really careful heating, because again, we're switching really fast, fairly low field strengths because it's pancake and all these other things. So it's probably never actually going to be applicable, but it made for some cool pictures, and it was a fun game to play. So we had a good time trying to get that done. So we were able to do all this stuff with channels, right? So the next question was, could we do the microcapsule one? And the cool part about the microcapsule, the challenging part of the microcapsule, was this is an aqueous solution. This is an aqueous solution. In fact, mostly they're water. And the normal way that you do encapsulation is you use an emulsion. So I have an oil phase core, I emulsify it, I put some chemistry into the water, it goes, and eventually it hits a critical molecular weight and crashes out to the interface and builds the polymer shell around the liquid drop. We can't do that with a water, because I'd have to do a water and oil emulsion. And I don't know if you've ever interacted with that, but they are difficult to stabilize. They're just difficult for a bunch of reasons. So we needed an alternative method. So we went to microfluidics. So we built what's called a flow focusing device, where we have 3 pieces flowing. We have a core material, an outer material which forms the shell, that becomes the shell of the microcapsule, and then a carrier fluid which sends it on. And so that's a real time. Now this is slow. And so it's made out of pipettes that you pull. We do it under a microscope, and basically the shell material flowing on the outside here is a UV cured polymer. And so what we did is he built these devices, visualized them using the microcapsule, and then we bought a fingernail acrylic curing system off of Amazon, and then built our own UV curing system as a result of that. So there was a bunch of processes and challenges associated with this, but in the eventual, we were able to encapsulate water, an aqueous solution inside this material, and I think this is the first time sort of pure water had been encapsulated using a microfluidic approach too. So that was fun. So what we were able to do is take the base solution and the iron salt solution. You could crush them, and they would form nanoparticles, right? And then we could embed it, and you could sort of see these nanoparticles. There's a bunch of details associated with the having to tune viscosity and all these other things, and porosity that I'm going to gloss over if you are, or I'm not actually going to address. So if you're interested, you can talk. But this was, needless to say, this was a non-insignificant undertaking, but the end game was we were able to produce both of these microcapsules and produce an effect. So one of the challenges that we ran into was getting them to fracture, right? So for the damage-triggered release of particles to be, or of core fluid to be successful, the core has to stick to the shell, to the matrix, right? And when I break it, it has to go through. And so we spent a lot of time optimizing our shell thickness to get that to happen. So what you can see here, right, this is the shell material, right? You can see that interface between the epoxy and the shell, and then some broken shells, and then holes where the shells were. This flips in and out for me, it's maybe sticking out, and I think it was sticking out. But once we got that done, we were able to demonstrate some damage detection, right? So this is a thin material, right? We scratched it, and then you can see those nanoparticles form along that scratch, right? So we were able to take the 2 nanoparticle species, flip it in there, scratch it, and then demonstrate that the healing, or the sort of damage detection occurs. We tried to do some damage detection in some TDCBs. Unfortunately, we could never, in this particular case, in these 2 cases, generate enough material to be magnetically detectable. That was sad. We tried doing it in Impact. So this is kind of what it looks like in fabrication. So what they did is they laid it up, sprinkled. It took them about 2 weeks of steady, like 6 or 8 hours a day, running these flow focusing devices to get enough microcapsules to actually make a sample. Again, a lot of time. And then we did some impact. We did a single impact, saw some color change, and then did a couple more impacts, try to break things up. Unfortunately, the amount of nanoparticles we generated, I think we just didn't have enough concentration in this case. We could clearly see the bruise, right? But we were never able to detect it magnetically. Though, oddly enough, we could take the panel, put it on a scale, and then bring a strong magnet down, and you could see the panel being lifted because the scale, right, the mass on that scale would go down. So sort of broadly, there was enough material there to be magnetically responsive. But our scanning system was really small, right? We were looking for high point accuracy when we were doing the initial scanning system, so it's only like the scanning sort of range is like 3 millimeters by 3 millimeters square, right? So the volume of material that we were interrogating was like a little bit too small, right, to actually get that. So that was unfortunate, but we still got a paper out of it because of the encapsulation. That was cool because that was an undertaking for sure. Okay, so what do I do with this thing that I can do, right? So I can make composites that have a vasculature, right? I'll be fully, I pulled that idea from somebody else. One of the things that we were able to do, or what has been sort of developed, is a sort of more advanced way of making those channels that you saw me pull the wires out of, right? And what we wanted to do was see if we could apply this to concentrating solar power. So, right, so there's like 2 ways to make energy from the sun, right, in general. First way is the solar panels, right, we're all familiar with that. The second way is what I refer to as the large, sort of like the large magnifying glass approach, right, where I have a central tower, I have a giant mirror field. This is out in Nevada. So this is an installation out in Nevada. I think this is a molten salt system. And so this is called the heliostat. And so all of these mirrors focus about a mile in diameter circle of mirrors of sunlight onto a single central tower, and it heats the working salt material up there to 400 or 500 C, and then we use that hot molten salt material to run a standard steam generation power cycle. There's a bunch of other sort of approaches. One using a direct gas phase. So this is using a standard steam or heat cycle. If you use supercritical CO2, you can run a Brayton cycle. So a Brayton cycle has a much smaller turbine, possibly higher efficiencies, but you have to be at higher temperatures. But the cool part is they have to detune these things to keep from burning up the central tower. because you can get 800, 900 C, no problem, right? But the molten salt's 400, 600, right? That's about as high as you can go. So there's a couple of different ways to do this. One of the ways is what's called a cavity receiver, where they have an Inconel tube running through there. They run supercritical CO2 through it. The Inconel heats up, and then the CO2 heats up. That's nice. Metal, high nickel alloy metals. Metals are not really like good absorbers, right? They tend to reflect. So we thought, can we use this same microvascular approach in a carbon-carbon composite to serve as a modular receiver? So we're going to build a synthetic network inside a composite that has a carbon fiber reinforcement in a carbon matrix. So it's, first off, it's like essentially black as color, right? So it's highly absorbing. And it's a carbon-carbon composite, so it's super light and relatively strong and has pretty good thermal properties. This structure is limited by the creep performance of the Inconel. At 500 C or 600 C, like Inconel creeps pretty bad, right? And so they have to be very careful in how they manage that to keep it from creep failing. And the other way that we're interested in, sort of, again, drawing on another group, we were going to build these in sort of small modules and connect them together. So if one of them fails, you just swap one. So the way that we did it is through this carbon-carbon composite. So these are derived sort of from pyrolyzed polymer matrix composites. That's what PMC stands for. So you take a standard polymer composite and you burn it. You burn it down to carbon. And it has, again, carbon-carbon has excellent material properties at relatively high temperatures, above 1,000 C. But it must be component to reduce oxidization. So if you take a carbon material and you heat it up to 1,000 C in air without anything on it, right, it burns like a candle because it's carbon. Which is an advantage if you're doing thermal management, right? So the space shuttle, the nose cone, and the leading edges were carbon-carbon composites because they would also, in addition to being strong and lightweight and highly heat resistant, they would ablate, right? So as they burn, that's a way to manage heat, right? So you're taking the heat away in the ablation process. They also make rocket nozzles out of it. Most commercial aircraft have carbon-carbon brake pads, right? And then you can just build complex structures out of them if you want to. So this is from Across Composites. This is from some random vendor on Alibaba, and this is on a journal article. So what we do is we take PLA. So this is polylactic acid, the same cheap filament that you would buy to do 3D printing. And the cool part about PLA is if you heat it up to about 250 C, it depolymerizes. So it goes from being polylactic acid back to lactic acid at 200 C, or lactic acid. At 200 C, that's above the boiling point of lactic acid. And so you heat it up, it depolymerizes into a gaseous phase, and then you evacuate. It's gone. And so we take this little 3D printed PLA, we vacuum bag the material, then we carbonize it at 1,000 C, and we graphitize it at 2,400 C, and you get a structural material that has a clear channel. And so right now we're in the process of continuing this. So this is an active project that's going on, and we're seeing most of our time is spent learning how to process this material, right? It's sort of a challenging thing to do. And then we spend a lot of time, one of the challenges with graphitization is you can see these cracks, right, in the edge. And so what happens is you graphitize it, is there's a phase change from the sort of amorphous carbon to a graphite structure. There's a volume change associated with that. And so it cracks. So you have to go through a bunch of cycles of densification. So you pyrolyze, you graphitize, you densify, you pyrolyze. You densify, you pyrolyze. Then you graphitize, then you densify. So you go through all these steps. So this little like 1/2 inch by 1 inch long single channel specimen has taken us, takes about 2 weeks to make, right? Process. So I guess the take-home message is Keller's lab makes you do the same thing over and over and over again for very long periods of time. So that sucks. But so this is really exciting, though. The thermal conductivities that we're getting on this are slightly above Inconel right now, and so we're in the process of actually doing characterization as well. The sort of next thing that I'm working on using this idea is actually in collaboration with Professor Yunus is to try to create self-healing membranes for pneumatic controllers for oil field sites. So one of the challenges that happens right now in sort of like an economic loss is there's quite a bit of methane release, right? Natural gas release from gas processing substations. or gas transportation stations. And this paper from 2015, if you look at it, so this is a leak rate versus sort of device percentile, right? So the team went out, did measurements at sites on pneumatic controllers, and we're measuring methane release rates per device, essentially. And what they found was that, not unsurprisingly, a small percentage of devices in this upper right-hand side was releasing like, 50% of the total unintended methane release. Right? And when they looked at it, these were mostly damaged. So for a lot of the controller systems, they use the natural gas, or can use the natural gas supply side, or the pressure in the transportation pipe as the control pressure, right? To use the pneumatic, to actuate the pneumatic actuator. And so if you have a damage in any system, any part of that system, you've essentially vented the transportation pipe straight to the atmosphere, right? And so this is actually a pretty low-cost way to get rid of something that is releasing sort of an intense greenhouse gas, but also an economic loss as well, right? If you're venting a lot of your product to the air, you would rather not do that because that's a product you can't sell. Anyway, so this is just some stuff about how that's good. So this is our goal. So what we wanted to do is try to create a self-repairing membrane to reduce that leakage. So this is sort of a cross section of a very simple pattern. And so what you can see here is, right, here comes the flow comes through, process through this sort of valve piece, and here is the connecting line, right, that provides pressure to actuate this. And so there's a large motor diaphragm here, which is a polyurethane elastomer or semi-rigid polyurethane material. There's a pilot membrane here, right? Either of these get damaged, you now have a direct vent to the atmosphere, right? And so our goal was to go ahead and use a microcapsule or microvascular, and I'll focus on a microvascular approach to create a self-healing membrane to go in there to seal up any damage, right? So what happens is it flexes and you get a crack or a tear, right, in your membrane material, and then suddenly you're venting. So this is just one part of a two-part project. The other part is to create an integrated diagnostic system where we're trying to take available data on either the actuator or sensors around this particular system to help us provide feedback on the health of this structure, and that's what we're talking about. So we use, again, we actually add a catalyst to that PLA filament that you saw from the previous one. So we're using the same approach, and we do that because that lowers the depolymerization temperature by quite a bit. We print it out, and then we thermally depolymerize it once we put it in an elastomer membrane. So this is a pretty simple pilot. So basically, we're using silicon rubber right now because it's got good high temperature performance, and we can access quite a wide range of mechanical properties in silicon rubber. We're working on trying to get it to a polyurethane, but the thermal stability of polyurethanes that we have easy access to has been challenging. So what we did here, right, so the grad student built this sort of interdigitated network where we could flow part A of a healing chemistry through one channel and part B through the other one. We depolymerize it, so you can see this is prior to depolymerization, and you can see that white PLA that's in there. Then it becomes fairly clear. We can flow. This is just colored water, just to demonstrate the process. It has, we had to vacuum out this so it's air, but then you cut across it, right? It bleeds out like you would expect it to. So how does it do in healing? It does pretty well. So we do a pressure test. So we have a pressure cell that we built. We put a sample in there, apply pressure on one side, and measure the output, right? And so if we apply 100 psi, there's 0 psi on this side, rut gauge pressure, right, relative to the atmosphere, then 100% heal. Good to go, right? This is a closed volume. If there was a leak, right, this pressure would slowly increase over time as gas leaks from one side of the membrane to the other. So what we have here is just some example plots. So this is time versus pressure, and so this is the control signal. So this is a pressure on this side, and this is a no heal. So right now we have a little bit of a pressure differential across that. So that's sort of something that we're a little bit interested in. It could be pressure drop, literally. But this should technically go. I actually think what's happening is we're leaking a little bit around our seal. This is a partial heal, so we go a little bit longer before it breaks through. And you can't see it, but there's a complete heal here too, where we never see any pressure increase. It's right on the bottom. So we run several samples, and the way that we actually think about healing in this case is how many percentage of the samples actually heal, right? And so so here, right, we have an fairly low inlet pressure, we get 100% healing. And then at some point in time, right, we start getting limited by our bond strength. So the healing relies on that adhesive bond, right, between the chemical that we've put into those channels that's leaked out and polymerized, and then we're loading it, right? So at some point, if the bond isn't particularly good, it tears again, right? And we get some. And so as we increase pressure, we start seeing a decrease in the percentage of specimens exhibiting 100% heal. And so things that we're sort of working on here is trying to improve the healing chemistry, so adding adhesion promoters and other sort of things to improve the bond that we get, improving the design of the channel network to try to be more realistic. We've gotten to the point now where we're basically making material to go into a commercial valve to do some sort of semi-pilot testing. And anyways, but we were pretty psyched about these results. So hopefully we'll get them into a membrane or get them into a system and sort of help reduce the amount of fugitive losses that we're seeing. So just a summary, we can demonstrate the ability to magnetically locate self-healing. It also demonstrated the ability of a vascular composite to actually mitigate damage via magnetic nanoparticle formation. And then a successful implementation of a multimodal damage detection approach. And then also we've been able to encapsulate an aqueous-based component and demonstrated the in-situ formation of magnetic nanoparticles. Both, I think, are firsts. And then we've, in the DOE thing, we've done an initial specimen development for this carbon-carbon composite. So we've got a sort of a demonstrator. Next step is to spend a lot of time characterizing that, seeing what type of material we are and where we can change the processing to improve it. And then also initial demonstration of self-healing for membrane materials in these pneumatic actuator systems. So that's been a pretty exciting set of stuff that we've accomplished last few years. So so thanks go to Matt Krall, who's now a postdoc, or actually I think he may be a staff scientist now, so he graduated a couple years ago. So we got fast tracked on the staff scientists at Los Alamos. I have a couple of postdocs that are helping with the carbon-carbon composite and the membrane materials, so Vahid Danakatai and Mahfouz Khan. JT, wasn't in here, Laura's now, is at Jardim. Laura did a little bit of work with the microcapsulations, now a postdoc in Kentucky. And then my current group, Caroline, Jonathan, Mark, and then some collaborators, Tato Tanakar at Boise State, Hema Ramstern in chemical engineering here at TU, helps with carbonization. Jim and Rami at your department that are co-PIs on the pneumatic actuator and self-healing grant. And then the sort of people that have sponsored the work that goes on in my lab. And so thanks for your attention. I'm happy to take any questions.
So questions?
Excuse me. Yeah.
Hi, Dr. Keller. I see a lot of channels in the self-healing materials.
Yeah.
Will these channels change the entirety of the materials?
Yes.
Like the strain?
No, for sure, right? So, so anytime you introduce, especially a hollow channel, right, that's a defect, right, for sure. So we were doing, there's a couple of ways to address that. So first one, right, is we again look to nature, right? So your bones do pretty well, right, even though they're full of holes, right? You have blood vessels through everything. The way they do that is preferential reinforcement around the channels, right? So there are ways that we can think about sort of when I put the PLA in, right? Think about coating the PLA in perhaps a different material, like nanoparticles or something to locally reinforce the channels, right? So that's a possibility. Or the idea is to skip it entirely, and instead of putting it in plane, you go vertical, and you go through plane, right? So the in-plane material properties in composites are usually the most important, right? I'm interested in being able to, be highly resistant to in-plane loading, less so to sort of through thickness loading. So if you sort of switch the idea, put the channels vertically through the material, you can still access the layers between the composite, which is highly important, but you have less impact on the in-plane properties, right? So clever design can be a way to address that. But you're absolutely correct. It's a problem. It's an issue. But we have, one of the cool parts about this approach is it was the same issue for those when I mentioned the fiber sensors, right, that they had. They're quite large. They have different material properties than the surrounding material. And so they tended to reduce the material strength. But there wasn't anything they could do about it, right? You had these fibers, they were there. They could do some coating, but there was a little bit, it never really worked very well. Because of the way that we're integrating these fibers, we have the opportunity to think about tailoring the materials specifically around those channels to improve their strength. And so there's a lot of knobs that we can turn that we haven't really turned yet to try to understand what the best way to do it is. The other option is to drive them smaller, right? We have that opportunity where the fiber sensors had to be a specific size, like by physics to work. The channels, essentially, we could drive them, as the same size as an individual carbon fiber, and then their impact, literally, in this case, becomes much less, right? Because they're just small.
Yeah, thank you.
Yeah, it's a good question.
Petroleum engineers. Yeah.
Yeah.
I have a question about the particular visit of this regeneration of the diamond. Can we use it like for infinite number of times? Or?
So for the for this type of thing, sort of barring complete blockage of the supply channel, right? Sure. The short answer is problem, right? Yeah. So I mean, there have been there's been studies done on structural composites with vascular networks where they've done repeated healing 30 or 40 times, and they just quit because they've done 30 or 40 times, it's enough, right? So but those were for like coating repair, right? So they had a vascular substrate with a coating on top. They'd crack it, fill in the repair, put it back, crack it, repair, crack, repair, crack, repair, crack, repair, right? So there was a possibility you were blocking the channels, right? But there was never really any damage to the channel substrate, right, with that thing. So the answer to that is it's a little unclear. Definitely more than once, probably less than infinite times, probably tens of times for sure. But I'm not really sure the answer to your question, and it hasn't really been explored.
What happens if the channel gets bent?
Yeah, that's it, right? Like that would be the problem, right? Yeah. So essentially, as long as I can like have access here and continue pumping blood, so to speak, through it, right? Like infinite. As long as somebody refills the reservoir, right? We could be infinite. So the fail is going to happen when a channel gets blocked, and there can be no longer any flow, right? So it's just like again, back to the human body, right? So you're good until until the blood vessel in your brain clogs up because of either been eating too many burgers or you have you've thrown a clot, right? But then badness happens, right? So it's a sort of similar situation. Right? Yeah. It's a good question. Both of those good questions. Thank you for going right at the weaknesses. So, anyway. Cool.
So I've got a question. Mike.
Yeah, sure.
A question about scale.
Yes.
So applications at larger scales. I'm thinking like rock.
Yeah.
Is there activity sort of
Trying to look at scaling this to
fractures?
Yeah. So the 3D printing thing, ostensibly, right? To be fully honest, this might be the first engineering application of this approach, right, that I've seen. So the first engineering application of the microcapsule approach is paint, right? So we create self-healing paint, so especially for marine systems, right? So offshore oil wells, ships, things of that nature, right, require frequent paint maintenance just for corrosion mitigation, right? And so if you create a self-healing thing, then that's at scale. It's easy to do, right? The channels are a little bit more complicated in implementation, but maybe not in actual reality, right? You just have to find something at scale, right? And then integrate it into a manufacturing. It's a manufacturing challenge more than anything else, right? So this is sort of uniquely okay, I think, especially in for this particular approach, because the membranes aren't that big. They have a injection molding process or some sort of reaction molding process in place. And so like it seems like you should be able to integrate these rather quickly at that sort of, I don't know, medium scale, right? You think like a foot, right, or something. Anything beyond that, I don't know, to be fully honest. I mean, we're pretty good at robotically doing things in composite layup at this point. So the answer to that is probably shouldn't be an issue, but the issues that were raised, specifically with the in-plane material properties and like that, have to be addressed before it moves onto aircraft, right? So that's why self-healing is the same way. Part of the reason I was interested in magnetically concentrating those is it does have an impact on the modulus. It tends to lower it, right? So a goal would be to minimize that globally, right? You know, unfortunately, probably locally, there might be other issues there, right? But try to minimize the global impact on elastic properties while maximizing the sort of repairing effect, right? So there's always, so that's why they go to paint, because there's almost no consequence of failure there other than you have to paint it. So I think, you know, that's an interesting, you know, place where they're sitting and trying to figure out like how to jump this from here to here to the next step. And I think that sort of the engineer, like the sort of gee-whiz material science piece is maybe starting to get out. And so the place that I'm sort of personally in my area focusing on is sort of the engineering applications and how to make those jumps from there. Cool.
All right. Quiet group.
Sorry. And now for something completely different, I guess, maybe. But anyways, well, thank you for your attention. I appreciate it. And I'm standing between you guys and the weekend, maybe, depending on how mean your advisors are. All right, sounds good. Thanks again, guys.
Thanks, Dr. Keller.
Just stop the recording here. Maybe. Why is this not working? Wait a minute. Oh, there it is. Nope. Nope. Jeez. Okay. I have not used Blackboard in a while, so I'm forgetting what to use.